Hey, my super chemist in Chem 112. This is Tracy Folks, and I'm upside down, ready to talk to you about Chapter 15, Chemical Equilibrium. I think in a lot of ways that Chapter 15 is easier than Chapter 14, for me personally. And I think you're going to find it to be that way as well. All right, so equilibrium. What is equilibrium? Okay. Well, it sounds like it has the word equal in it. So equal means same. So it must have something to do with that. And what equilibrium is when you have this double-sided arrow here, it means the reaction goes both ways. It's going back and forth and back and forth. And when it's at equilibrium, the rate that it's going this way is equal to the rate that it's going this way. It's equal. The rates are equal. It doesn't necessarily mean that the concentrations on both sides are equal. It's just the rate or the speed going this way is equal to the rate of the speed going that way. Okay? And like all chemistry, we have a little bit of math to go with it. And that is called the equilibrium constant. Okay? And when I think of the equilibrium constant, I know in your textbook and I know in the slides I gave you this formula. I just kind of remember products over reactants. And the equilibrium constant is symbolized by the letter K. Okay, K just is the equilibrium constant. So a couple of examples, and these notes can be found in Schoology along with the video. So if I ask you to write an equilibrium constant, and that's not very dark, but these are the examples that are there. If I ask you to write an equilibrium constant for me, the first thing I would write on the paper is K equals products over reactants, because that kind of gets me on the right track. And you should know by this point that this is the product side and this is the reactant side. And here's how you write it. You use those concentration brackets. You use brackets to show concentration. And you put the substance in the brackets. And whatever number's in the balanced equation, that's your exponent. Okay? And so over here, I have that, and I have that. And those concentrations are going to be in molarity. Okay, so when we start putting numbers in, just kind of be prepared to see biggie M after some numbers. But that's it. That's all an equilibrium constant is. Okay, products over reactants. Super duper easy. Now, what is the significance of this K value? This K value is going to start to get some numbers. We're going to do some examples where we plug and chug some concentrations. Now, the significance, and see, you can see it's in your slides there. The significance is if K is really, really small, like super small, smaller than 1, the reverse reaction is favored. So that means going to the left is going to be favored. If K equals 1, it's at equilibrium, neither side is favored. And if K is greater than 1, going this way, the regular way, the forward way, is favored. Okay? Now, let's do an example. So the next thing in your notes is a good old example. Okay, and so I am on this, oopsie daisy, this slide in your notes. And you know that you have A going to 2B. And I'm not putting the parentheses gas in there like there is on this just for time's sake, but just know these are all gases. I'll tell you when it changes, and it will change. K equals that. And I want to know what K is going to equal on this reaction, okay? So I'm giving you one K, and I'm asking you to find the other K, all right? So here's how I would solve that. I'd first look at it and say, okay, these reactions are flipped. This is the reverse of that reaction. B is on this side, A is on that side. So when I go to do this, When it's a reverse reaction and you're trying to solve for this new K value, it's going to be 1 over this one. And I'm going to put a little star here so we can, there we go. Now, I've taken into account that it's flipped. The other thing going on here is this reaction is halved, okay? So I've got to take all of this to the half power, okay? When I put this into my calculator, I got this to the half. Do we know how to put this in our calculator? The little caret 1/2, okay? For this reaction, K equals 10, okay? I put this K over 1 because it was flipped, and because it was halved, I made it to the half power. Okie dokie. Moving right along. You see me talking and thinking. All right. Equilibrium in terms of pressure. All right, so sometimes we think about equilibrium in terms of concentration, like molarity. And sometimes we think about equilibrium in terms of pressure, because pressure can change the dynamics of our reaction. Since if I have a high pressure, molecules are really close to each other, and the closer you are, the more likely you're going to react. And we learned that in chapter 14 when we talked about reaction rates. Now, we have here, it's a K value again, but there's a little p after that, and that p means pressure. And you set it up exactly the same way we've been doing, excuse me, mini stroke, products over reactants. Okay, and last time when I was showing it to you, we had the concentration brackets, and I expect there to be some molarity numbers. This time I'm going to expect there to be some pressure, some atmosphere, some millimeters of mercury, some torr, some kind of pressure units, okay? Now, the K that we did before, when I had my brackets, I wrote K. It's technically KC. C for concentration, KP, P for pressure. Well, what if I give you one and I want the other one? How am I going to find that? Well, as you read this chapter in your book, you know that the K of the pressure is equal to the K of the concentration, R, which is my 0.0821, my R from ideal gas law. T for temperature, that's going to be temperature in Kelvin. And then it was to this exponent of delta N. Well, I know that N is number of moles generally in chemistry, but what do I mean by number of moles? So if you look at the example on this slide, I gave you an equation. And all of these are gases. I'm not writing this, but what I'm doing is products minus reactants. How many moles of gas on the product side? 2 minus what's over here. 2 plus 1 is 3. 2 minus 3 is -1. So that's where that number is going to come from. I don't want you to just think I pulled it, out from nowhere. Now, when you look at this example, I tell you that Kp is 2.2 times 10 to the 12 at 25 degrees Celsius. All right? So when I go to put these numbers in, I'm looking for Kc. I know that Kp is that. Kc is X. R is that. T is 25 degrees. That has to be put in Kelvin, so I add 273 to it. So I have 298. And this R and this T are all to the power of -1. Again, caret -1 in your calculator. So when I solved for X, I got 5.4 times 10 to the 13. Okay? If you have issues solving for X, you can come and see me. Now, do you remember when I said everything here is a gas, right? So we don't have to worry about it. And I said, I'll tell you when it changes. It's about to change. Okay? So when you set up these K values and we do products over reactants, okay, you can use any substance in the product and the reactant side except solids and liquids. So if they have an S and an L or an L after them, you can't use them. All right? And what that's called in your textbook is heterogeneous equilibria. Okay? And I'm going to do an example on the board just so you get an idea of what I'm talking about. So if on a test or quiz or a calculation sheet, I said, hey, write the K equilibrium constant for this. All right, when I do it, again, I just do K equals products over reactants. That kind of keeps me straight. And then I look at the equation and I'm like, all right, can't use any solids or liquids. So I just cross them out because I'm visual. I need that to keep me straight. And so now on the product side, I just have this and that. It's that easy. You just cross it out if it says solid or liquid and you do not include it in the K value. Okay? Heterogeneous equilibria. Super duper easy. Now comes the fun and exciting math. Okay? And so now we're going to take these K values and we're going to start to kind of use some numbers and figure out what some initial concentrations are, what some equilibrium concentrations are. And it is going to require you to be somewhat methodical when you do it. There are no shortcuts. I've been doing this longer than you've been alive. I don't take shortcuts, okay? So if you look at this example in your notes, a reaction mixture at 780 degrees Celsius, that is just there for no reason whatsoever, okay? Initially contains CO concentration of 0.5 and hydrogen concentration of 1. What's the value of the equilibrium concentrations? So on the paper you would be using, you would have the equation already written. And they're all gases, so I don't have to worry about any crazy poo stuff. And then when you're asked about equilibrium concentrations, I like to draw a little table, okay? And on my table I have all of the items in my reaction. Okay? And I put the numbers in the balanced equation there because they're going to be important. And then let me make sure I'm still, I'm okay. Then I write ice. Initial, what's the change, and what's the equilibrium value, okay? And so I can read from my problem that the initial value of CO was 0.5, so I put it in. And the initial value of the hydrogen was 1, so I put it in. And now I'm going to go ahead and I'm going to figure out what the change is. It says, what is the value of the equilibrium constant? Well, the equilibrium constant is going to be K equals that over that. Products minus reactants. So we're going to use this table in just a minute to determine what the value of K is. It looks like I am eking close to my 15-minute cutoff, so I'm going to have to pick this up in part 2 of Chapter 15 notes. See you there, guys. Toodles poodles.